Hello and welcome back to some more organic chemistry. Today we will be covering some of the special reactions that we have for ketones and aldehydes. Now, I should probably call this series the Summary of Reactions series. I feel like that would make a great title for a playlist where we just summarize all the reactions for different types of functional groups. So, let's get started. For now, let's start off with a special reaction called the Wittig reaction. Now, how do we perform this reaction and what's the purpose of it? Well, what it does is it converts a carbonyl group into an alkene. And this is really useful because it provides an alternative to an E2 reaction. The E2 reaction previously would provide side products and we would have to do many things in order to avoid those side products. But here with the Wittig reaction, we can make sure that we get one certain product plus the cis and trans isomers obviously, without having to worry about side products. Now, how do we do this? Well, we have to provide something called an aldehyde. It's spelled just like this, but pronounced aldehyde. And how do we grade this? Well, first you get an alkyl group that has a good leaving group, such as a halogen, and at least one hydrogen. You provide it with triphenyl phosphide, and what happens here is that it will connect to the carbon through an SN2 displacement, where the good leaving group will leave and just remain as a salt. This whole process will create a salt. So you have a positive charge on the triphenyl phosphide and a negative charge on the leaving group. And these two together are called the Wittig salt. And so let me write that down. Wittig salt. And if you provide it with a strong base, this strong base such as butyl lithium, it'll abstract the hydrogen, at least one hydrogen from that carbon, and leave it with a negative charge. Now notice this is a very strong nucleophile, so it's very likely to attack the carbonyl group at the carbon with the partial positive charge, which is the one connected to double bonded to the oxygen. So for our ketone, we get this intermediate right here. We have an oxygen and it has a negative charge. And notice how we didn't provide an acid, and so it's not an alcohol group, it's just an alkoxide. And the carbon that connected to it with a negative charge has its R1 and R2 group. Let me put these to the side. So R2, R1, and then it has its triphenyl phosphide that has a positive charge on it. And same thing goes for the aldehyde. So let me show that. Negative charge here. Then we have R2, R1, and our triphenyl phosphide. Now, something interesting happens. This oxygen and phosphorus, they're attracted to each other. And so what happens is that the oxygen will form a ring by connecting one of its lone pairs to phosphorus. And so after this ring is formed, it's also likely to break right off the bat. But how will it break? The way it breaks is that oxygen will break its sigma bond and form another bond with phosphorus. And then the sigma bond between our carbon from the aldehyde and the phosphorus will break and form a pi bond between these two carbons, the carbon with the carbonyl group and the carbon between the aldehyde. And this forms this final product. And so I'll draw the arrows the same thing for the aldehyde. The mechanism is exactly the same. Over here and over here, and we get this. Now, since we're going to form a double bond, we get both cis and trans isomers. So we have here, I'll write R1 and R2, and then plus other isomer. And then same thing goes for our aldehyde. Over here, we have our hydrogen, double bond, R1, R2, and then our other isomer. And so this is the Wittig reaction, and it provides really good yields of these alkenes. Now, let's cover the next type of special reactions that we have when it comes to ketones and aldehydes. And this is imine formation. So I-M-I-N-E, imine. Now, what is an imine? Well, this is basically a carbon that's double bonded to a nitrogen. This is an imine group. Now, how do we form this? Well, if we provide just some sort of acid with this amine, as long as it's at a good pH. So if we have a pH of around 4.5, this is the most stable pH in order to form an imine. What happens is that the lone pairs on the ketone and the aldehyde on the carbonyl group are attracted to the hydrogen and they'll get protonated. So if you have an acid, it'll protonate these groups and make the carbon connected to the oxygen a really good group to be attacked by the amine in an SN2 addition, so a nucleophilic addition in this case scenario. And so for our ketone, we get this. We have an OH group over here, and we have a nitrogen, and after the nitrogen loses one of its protons, in order to maintain a neutral charge, it'll look like this. And for the aldehyde, it looks like this. We have our nitrogen after it gets deprotonated, and then an R group. Now this intermediate is called a carbonyl amine. So carbonyl amine. And it's pretty unstable. And so the alcohol group in this carbonyl amine is likely to get protonated once more and leave, and then nitrogen in that scenario will use one of its lone pairs and form a bond with the carbon, which is a second bond essentially, and basically create a double bond with that carbon, a pi bond. And then again, it'll have a positive charge obviously, and so we have to deprotonate that hydrogen that's connected to it, and we get this final product for our ketone, which is this right here. And for our aldehyde, we get this final product, which is with the hydrogen over there, double bond, nitrogen, and R group. Now, if this R group is just a regular hydrogen, it's an amine. If it's a carbon chain, what ends up happening is that not only is it an amine, but it has a special name called a Schiff base. And so this can work as a base. And obviously this process is actually reversible. If we just add acid or an excess of water, we can reverse this product back into its ketone and aldehyde derivatives. Now, this R group right here, if it's an OH group, what ends up happening is that we end up calling the product an oxime. And if the R group is another nitrogen, and notice how this is hydrazine, we have our final product called hydrazone, almost like ketone. And then if we have a phenyl group on that hydrazine, it's just called phenyl hydrazone. And then finally, if we have this group right here, the final product will be called a semi-carbazide or carbazone. Now, our final special reaction is called the Baeyer Villiger reaction. Now, what's the point of the Baeyer Villiger reaction? Well, say you have a ketone or an aldehyde, but instead of creating an amine or an alkene, you want to create an ester. How do you do that? Well, provide it with a peroxy acid. This peroxy acid, since it's an acid, will have the lone pairs on the ketone or the aldehyde attracted to it. So let's just start off with the ketone reaction. This oxygen gets protonated. The carbon connected to it becomes an easy target, and so one of the oxygens on the peroxy acid will connect to it, and so we get this intermediate right here. We have our carbon, our R1 group, our R2 group, and then we have our first oxygen from the peroxy acid, the second oxygen, and this oxygen is the one that originally had a hydrogen on it, but it lost it due to the protonation. And then we have a carbon over here, double bonded, and the rest of the chain. So that's our peroxy acid group right here. Now, if we have a solvent that can deprotonate this hydrogen from the alcohol group, one of the lone pairs on the oxygen is going to try and form a pi bond with that carbon. And so what happens over here is that the carbon can't have 5 bonds, so it has to break one of its bonds. So what happens? Well, we have something called a migration, or like a methyl shift. A methyl shift is a type of migration. Now we have our R1 group and our R2 group, and which group is going to be the one that's going to migrate in this scenario? Well, if the R2 group is larger than the R1 group, the R2 group is going to migrate. And so in this scenario, we're going to have the R2 group break its bond from the carbon and attack that oxygen that was from the peroxy acid. And then this bond breaks over here too, and we get this product right here. So we have our R1 group, carbon, double bonded to an oxygen, the oxygen from the peroxy acid, and then the R2 group. And this is our ester right here. So that is the Baeyer Villiger reaction. And we notice that the migration occurs with the larger group. Now, how is it different from the aldehyde? Why did I say let's leave the aldehyde later? Well, it's not because the mechanism is any different. However, but it's the preference for what should migrate. Notice how we have the larger group is the one that's going to be the one that's migrating. So if this is secondary, for example, and this is primary, the secondary group is going to migrate. However, there's also something attached to it. No matter how big it gets, a hydrogen will always be the one to migrate first if it exists. So if we have a hydrogen connected to the carbonyl group, which classifies it as an aldehyde, the hydrogen is always going to be the one that's going to migrate. And what that creates is this product right here for this specific aldehyde. And notice that this is no longer an ester. This is actually a carboxylic acid. And so the formation of this carboxylic acid is preferred over creating that ester. And so This is the Baeyer Villiger reaction. And to summarize, a hydrogen is preferred over a tertiary group, which is preferred over a secondary group, such as a phenol. And then this is preferred over a primary, which is preferred over a methyl, which is just a carbon with 3 hydrogens. And so that is your special Baeyer Villiger reaction. And that summarizes all the special reactions that we have for ketones and aldehydes.